Welcome to this explainer. Today we're decoding Nigeria's 2026 Forest Reference Emission Level Report, or FREL for short. Honestly, this document is an incredible piece of scientific detective work. We're going to look at exactly how a nation measures its environmental pulse and the absolute lengths scientists go to just to get the facts straight.
So let's dive right into the massive question at the center of all this. Think about the sheer scale of Nigeria for a second. We're talking over 92 million hectares of incredibly diverse landscapes. You've got dense tropical rainforests all the way to sprawling savannas. So how do you actually track the changing trees across all of that land? Well, as you'll see, it takes a really fascinating blend of cutting-edge satellite tech and painstaking human analysis to get it right.
Here's our roadmap for today. We'll start with the climate benchmark, move into upgrading the system, look at the meticulous investigation, see how they're catching the errors, and finally look at the final tally.
Section 1. The Climate Benchmark.
Okay, so the absolute most crucial point here is that a FREL acts kind of like a fitness tracker, but for a country's climate goals. You absolutely have to take an accurate baseline measurement of your emissions before you can step on the scale and prove any future progress to the international community. In the world of global climate policy, without a precise, verifiable FREL, your emission reduction claims basically don't hold water. Now, Nigeria took a really smart, stepwise approach to get this right. They didn't just guess out of nowhere. They started with a sub-national pilot in Cross River State back in 2018, and then scaled that up to their first national FREL in 2019. Now, with this revised 2026 submission, they're shifting to a highly accurate 5-year reference window, spanning 2017 to 2021. And this is key, because it ensures the data reflects the most current real-world deforestation dynamics.
Section 2. Upgrading the system. You really have to notice the evolution of their tracking system here. The older 2019 FREL only tracked outright deforestation, where the forest is completely cleared, and it only measured carbon dioxide. But this revised FREL, it's way more sophisticated. It actually adds the tracking of forest degradation. That's a real game changer, because degradation is where land is technically still a forest, but it loses biomass and quality, maybe from selective logging or brush fires. Plus, they're now tracking non-CO2 gases, specifically methane and nitrous oxide, released from those fire-related degradations. So we're getting a much more complete picture of what's hitting the atmosphere.
Section 3. The meticulous investigation. To actually pull this off, the team overlaid a vast systematic sampling grid right across the map of Nigeria. We're talking an 11.2 by 11.2 kilometer spacing, covering every single ecological zone evenly. This is literally textbook scientific rigor. It's designed specifically to avoid any sampling bias. Because, you can't just look where you expect to find a problem. You have to look absolutely everywhere. 7,419. That is the staggering number of sample points plotted across that national grid. And remember, each one of these individual points required a human analyst to painstakingly review satellite imagery to figure out exactly what was happening on the ground. Let's zoom all the way in from that massive national map down to this exact 0.5 hectare satellite view. This kind of puts you right in the seat of the data analyst. On the top, you're looking at dense, unbroken forest canopy in 2012, but below it, the exact same square in 2021, clearly showing a change event. The land has just been cleared. So the analyst's job is to spot these transitions, mark the exact year they happened, and identify what the land was converted into.
Section 4. Catching the errors.
Analysts use these really precise, multi-purpose survey tools within a platform called Collect Earth. They had to log land use, identify subclasses, and flag any degradation events, like fires or logging. But here's the thing. Interpreting the complexities of nature from space is naturally going to lead to some disagreements. I mean, what one person calls sparse forest, another might easily call savanna woodland. Add in human fatigue, and vigilance errors are just inevitable. And that brings us to the plot twist of our investigation. On the left side here in round 1, those light colors show low pairwise agreement among the interpreters. Basically, they were disagreeing on how to classify certain land changes. But instead of just shrugging and accepting flawed data, they paused. They went back, did rigorous retraining, clarified all their definitions, and ran the samples again. Now look at the right side in round 2. All that dark blue, that represents a highly unified consensus. They essentially calibrated the human brain to act as one unified, accurate sensor. But they didn't just stop with human training. To guarantee absolute accuracy, they cross-examined the human data against global algorithmic data sets. They used what's called a convergence of evidence approach, checking their homework against global forest change maps. They also brought in advanced ESAB time series analysis, which is a fancy way of saying they use algorithms to calculate the exact probability that a piece of land changed. If the algorithm saw a high probability of change, but the human analyst said no change, boom, that sample was flagged. Ultimately, 1,536 flagged samples were pulled out, reviewed by a group, and reinterpreted to catch any hidden omission or commission errors.
Section 5. The final tally. Looking at the final data, it reveals a very clear geographic pattern. The Guinea's savanna takes the absolute hardest hit, with roughly 824,000 hectares lost during that 2017 to 2021 reference period. The derived savanna and the lowland rainforest follow right behind it, so this shows us exactly where the environmental pressure is most intense across the country.
But we have to ask, why is this happening? Well, the evidence points unequivocally to agricultural expansion. The conversion of forest into arable cropland is the absolute #1 driver of forest loss in Nigeria. This is followed by transitions to agroforestry and fallow land. It really paints a vivid picture of a growing population that desperately needs land to cultivate food, which is putting immense pressure on those savanna ecosystems we were just talking about. So it all comes down to this final, highly verifiable benchmark: 58,403,033 tons of CO2 equivalent emitted per year. That is Nigeria's official benchmark emission level from deforestation and forest degradation for the 2017 to 2021 period. Because of the incredible scientific rigor we just walked through, the international community can actually trust this number. As we wrap up this explainer, I want you to consider the massive leap forward this actually represents. We are officially moving from estimates and guesswork to high-tech, algorithm-checked, systematically sampled proof. So how will holding countries to these incredibly precise, transparent emission benchmarks change the future of global climate policy? When there's literally nowhere left for the data to hide, will it finally force real accountability on a global scale? Think about that for a second. Thanks for joining me on this deep dive, and I really hope you leave with a profound appreciation for the science of tracking our changing world.